Welcome students. So today we are going to discuss section 7.1, which is system of linear differential equations. So before we go, let's motivate ourselves with the pre-predator equations and see how the system of linear differential equations is applied. Okay. So Um, so consider the following closed ecosystem. So the ecosystem is closed means there's no migration allowed in and out of the system, and there are only two type of animals. One is a predator and the other one is prey. They form a simple food chain where a predator species hunt the prey, and then the prey basically grazes the vegetation and they increase or decrease, right? Now the size of two population can be described by a system of two nonlinear first-order differential equations, also known as, after their inventors, Lotka-Volterra equations. Okay? They actually originated in fish, they were studying the fish populations in Mediterranean after World War I. So what is it about? So let X be the population of prey species and YT denote the population of predator species. Of course, they are a function of time because they will change with respect to time. Now, so let's understand how will basically the population of prey species changes. So that is given by dx by dt, and that depends on the population of prey already existing uh, times, say, some alpha times xy, where y is the population of predator species. It makes sense, right? I mean, that the prey species will depend on not only how many are already there, but also how big is the predator population, right? Because if predator population is too large, suppose there's only one, so suppose there are 5 rabbits and there are 20 wolves, right? Then the rabbit population will diminish to 0 right away. However, if there are 1,000 rabbits and there's only one wolf, then you see the population, the rate at which the population of rabbits will change will be different. So of course, the rate of change of uh, the prey species depends on the both already the prey population and also prey population times some population of predator. Similarly, the population of predator will also change, right? And it depends on already existing the population of predator times, basically it has a factor, it has a multiple of X in it as well, because if there are no, for example, if there are no prey, the predator won't survive, right? So this system of equations, so you get two equations, right? So such is called system of equations. So we get two equations, so and they are linear, right? Sorry, they're not linear, my bad. This is part decides whether they're linear. So they're non-linear because you have X and Y multiplied together. However, they are first order because you have only first order derivatives involved in it. So this gives you a system of, of differential equations, and this is what we are going to study for this part of the lecture, right? So having that motivation in the background, it's meaningful. It's also applied in other branches of sciences. For example, it's applied heavily in evolutionary biology, obviously for the prey-predator relation you saw. It's also applied in chemical interactions, springs, where basically you have a spring system with multiple masses and so on and so forth. So having that motivation in mind, let's proceed. So definition. So let x1, x2, x3, xn t be the function of single variable t. So a system of n first order linear differential equation is given by the following form. So you'll have x prime, x1 prime, you'll have x2 prime, dot 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 xn prime, and they are related to all f of x1. So let's say t x1 xn, So let's call this as f1 as well. Then x2 prime is related to the other variables as well. Yeah, and xn prime. So dot 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 f2 fn t of x1 xn. Yeah, where fi is a function of t x1 all the way until xn. So this is what a system of n first order differential equation looks like, right? Of course, it's not linear because we don't know how f1, f2, f3, fn's are. Okay. So now, what would a solution to such differential equation would mean? A system of differential equation would mean a solution would be solution on an interval I is a set of n functions, right? Is a set of n functions. So essentially, the idea is you want to solve for x1, x2, xn, right? So it's a set of n functions. Let's call this x1 equals to phi1 of t, x2 equals to phi2 of t, xn equals to phi n of t, right? So that satisfy the system of equations or system of differential equations at all points in I. Now note that generally we'll have initial condition as well. So typically we have initial conditions. So typically initial conditions, and the initial conditions will be for each of the variables. So we have initial condition at t naught, say x1 of t naught equals to x1 naught dot 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 xn of t naught is equal to xn naught. Okay, so these are some constants given. Yeah. You can actually think about this as, you can also think about this equations or this solutions basically as what? So you can think of solutions. So how do you think about this? You can think about the solutions as a set of parametric equations in n-dimensional space. N-dimensional space, and yeah, so the solution is one-dimensional in some sense, right? Okay. All right. So as we said, as we already gave an example of pre-predator model, and there are other examples where this can be applied. One of the other applications is you can convert a single higher order differential equation into system of first order differential equations and solve it. You will say, is there any merit to it? Well, the merit is when you're doing some basically algorithms for solving ODEs numerically. We'll see an example. Okay. So now let's look at the following problem. The problem is you're given the second order differential equations and you want to convert it into system of two differential equations. So how do I want to write it? So let me call my x1 of t to be u, and then x2 of t will be u prime. So let's see what happens then. You will see that x1 of t is u and x2 of t is u prime. So now what do I get? So what my system of equation is x1 prime equals to something, x2 prime equals to something, right? So let's see here, what do we get? We get x1 prime equals to u prime, which is going to be x2. And my x2 prime is going to be u double prime. And what is my u double prime? From here, I can see that u double prime is minus 3u prime minus 2u. So this is going to be minus 3u prime, which is my x2, minus 2u, which is x1. So let me write down now my system of so what is the system we get? So we get system of linear differential equation is x1 prime equals to x2 and x2 prime equals to minus 2x1 minus 3x2. So this is how you get system of differential equation. Okay, so system of linear, but our goal is to study the first order. So I'll just write down first order. Of course, they are linear as well, but later on we'll make a distinction. So let's move on and generalize this idea, transforming an nth order linear, sorry, my bad again, nth order differential equation into n first order differential equation. Yeah, there's no discussion about linear here, all right? So again, the procedure of above can be done below here as well. So let's say, suppose you're given an nth order. So how is an nth order D given by? The general form is y1, sorry, y1, first y, then y1, dot, dot. This is how a general form of an nth order D is given by, right? So now, what we do is the following. We define x1 to be your y, x2 to be y prime, x3 to be y double prime, all the way until xn to be minus 1 prime, like this, right? So how will then you can write down the system now? So the system will look like, so system of first order equations will look like what? So first let me write down. So again, you want to write x1 prime, x2 prime, dot, 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 xn prime, right? So let's write that down. So we want x1 prime, x2 prime equals to something, dot, 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 xn prime equals to something. So let's see. So what is x1 prime? x1 prime is y prime. And what is my y prime? Y prime is x2. So this will become x2. Similarly, following the same way, we get x3. And we get xn prime is going to be, so xn prime is going to be my y n, right? So that will be derivative of this guy, and so this is yn, and yn is basically this part here. So this is going to be f of t. Now note that there is no y anymore, all right? I'm writing my system of first order differential equations in x1, x2, x3, xn. So I'll replace y by x1, y prime by x2, y prime by y double prime by so on until last one, which is going to be xn. So this is a system of first order ODEs, all right? And we got it out of an nth order ODE. And again, why do we do this? Well, there are some numerical algorithms where the system of ODEs is easier to solve than the original differential equation. All right, and now you can see, well, depending on your f is linear or not, this capital F function in linear in t, x1, x2, xn, we can say whether your system of ODEs, first order ODEs is linear or not. Okay. So that discussion will leave it to later, slightly later. So now let's talk about the existence and uniqueness. So suppose you're given for each I from 1 to n, you're given fi and dou fi by dou x1, blah, 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 are continuous in each of a hyperrectangle defined by alpha is less than t less than beta, alpha 1 is less than xn less than beta 1, blah, blah, blah. And suppose your initial point t naught, x1 naught, blah, blah, blah belongs to this hyperrectangle, then there exists a unique solution in the interval from t naught minus h to t naught plus h, yeah, which satisfies the given initial condition. So this is what the discussion about the initial existence and uniqueness is. So let's demystify this slightly. So what do we have to start with? You have, what are these FIs? So you are starting with, again, you start with x1 prime equals to f1 t x1 all the way xn, and then you have xn prime equals to fn t of x1 to xn, and you're given the initial condition at t naught. So we have x naught, x1 of t naught equals to x1 naught, and so on. You have xn of t naught is xn naught. Now, given these things, this piece of information, you're asked, does the solution exist? And if it exists, is it unique? So the existence and uniqueness theorem tells you the following. So for each each I, you consider f1. Now take f1 and suppose your f1 with respect to x1, f2 with respect to x2, f2 with respect to f1 with respect to x1, derivative of f1 with respect to x2. All these are continuous in a hyperrectangle defined around. So you see that this point is in the space, right? So let me just work with two uh, variables here. So what do I have? I have my t is between alpha and beta. My alpha 1 is between, my x1 is between alpha 1 and beta 1. And suppose my x2 is between alpha and beta 2. So what happens is the following. Because of the initial condition, I get a point in the space like that. And this point in the space and so in some hyperrectangle which contains what? Which contains my t naught, x1 naught, and x2 naught. In this sum interval, so instead of interval, we have a rectangle now. So in this rectangle, we'll have a unique solution for x1, x2, xn, right? So for some t, which is between t naught, some t between t naught minus h to t naught plus h, the size here is unknown of what the interval around t naught would be, in which we'll have a unique solution, but the solution exists. You can see the similarity between this equation, this theorem, and the theorem of non-linear differential equation, right? That they are similar because the interval is unknown. Now let's study the next kind, which is a system of first order linear differential equation. So what do you mean by linear? If each of this f1, f2, f3, fn are linear, then we say that the system is basically a linear differential equation. Okay, so what does it, how does a function which is linear, say suppose f1 t x1 all the way until xn is linear, how will it look like? So a linear equation, so basically in this case, if you want to say that this is linear, it will look like a some coefficient for x1 plus some coefficient for x2 dot 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 some coefficient. So a1, a2, an, xn plus some function, say g1 of t. So this is what we mean by this being a linear. Okay, so now how do I generalize it for if I have, instead of x1 prime, if I have all the way until xn prime? So such system is given by the following. Let me erase this. So we have x1 prime equals to x1 plus x2 dot 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 plus xn plus g1 of t. Now it's linear so that these coefficients are, so linear generally means the coefficient is constant, but linear over the function field of so we are basically discussing linear over the functions of one variable. So therefore here we'll have p11t, p12t dot 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 p1nt. So these coefficients are functions of t. Okay, so that's what we mean by linear. So similarly, for xn prime, you will have p. Now I'm writing the coefficients carefully. The labeling is careful. n t of xn plus gn of t. So where p11, so you know that you can see that pij's and gi's are independent of x1 to xn. Okay. Now, when do we call this system homogeneous? So we call this system homogeneous if g1 to g2 all the way gn equals to 0. Yeah, 0. Otherwise, it is, so all must be 0, right? All must be 0. Otherwise, we'll call this as non-homogeneous. Now, for linear differential equations, system of linear differential equation becomes easier. So if you have pij's and gi's as above are continuous on an interval I, which also contains t naught, then there exists a unique solution. X1 equals to phi of phi1 of t, x2 equals to phi2 of t, and so on. Xn equals to phi n of t. And what is this interval? So it will basically, if it is continuous on this interval, alpha to beta, then the solutions will exist on this interval, alpha to beta. All right. So connected with the linearity argument of first order linear differential equation, yeah, you'll see that they are very similar. So now this, let's see, this system can be written in a slightly different way. So this system can be written in, so I can write it as x1 prime, x2 prime, dot dot dot, xn prime, equals to P11, you see, you can write a matrix out of it, right? So this is going to be P11 times X1, P12, sorry, P12, P1N, Pn1, Pnn, Pn2 multiplied by x1, x2, xn plus g1, g2, gn. So you see, you can write a system. So you can write this system of equation in a matrix form. So it makes sense to understand now how to deal with matrices. So we'll build upon those in the next lecture. Before I go further, this can be written as, if you choose to call this matrix as P, this is a matrix now. If you choose to call this as X, as a vector, this is a vector G. Let's put an arrow to indicate that they are vectors. So you will get that X prime equals to P X plus G. Yeah, so now you see system of linear differential equations. Sorry, system of, that is correct, system of first order linear differential equations have a deeper connection with this kind of matrices. So now if we understand this matrix, we can actually tell a lot about the solutions. So that's what we're going to do in the next class. Thank you for your attention.